Rutherford scattered helium nuclei, that's an alpha particle, from gold nuclei. And by observing the process in which helium scatters from gold, he concluded that an atom consists of a tiny nucleus, positively charged, that will be the gold nucleus, surrounded by electrons. Now, the electrons have a small mass, so they don't affect the alpha particle very much. So the alpha particle just scatters in the gold nucleus. And this problem 30 from chapter 24, asks what kinetic energy is necessary so that the alpha particle will just touch the nucleus. So you're given the radii in femtometers. We always start with a picture. So here's a picture before the collision. The alpha particle is coming in with a velocity v0. The helium, the gold nucleus is just sitting still. Then at some time, they'll be just touching. And at the instant when they're just touching, they'll both be moving with the same speed, v1. And there are two conservation laws: conservation of energy and conservation of momentum. So here's the equation for conservation of momentum. Little m is the mass of the alpha particle. V0 is the speed of the initial speed of the alpha particle. That's the initial momentum. The final momentum is the combination of the two masses, little m plus capital M. Capital M is the gold nucleus mass times the velocity of those two particles. Momentum is mass times velocity. So that's one equation. The other equation is conservation of energy. The initial energy is 1/2 mv0 squared for the alpha particle. The final energy is 1/2 m plus m v1 squared for the pair of particles. But there's also now some potential energy. The potential energy, it's the energy of the electric charges. The alpha particle has charge 2. The nucleus has charge z. So the product of the two charges is 2 times z times e. So I see I have a mistake here. Two ze squared, that's the product of the charges, times the Coulomb constant, which we've used since the beginning of the semester, 8.99 times 10 to the 9th, divided by the distance separating the centers. Since they're just touching, that distance would be the sum of the two radii, which are given up here. So you have here two equations with two unknowns. What are the unknowns? The masses are known. The charges are known. What's not known? Well, the distance. No, that's known because that's just the sum of the radii. So that's... So what's unknown? Well, V0 and V1 are unknown. Now the answer to the question will be 1/2 mv0 squared. So after you solve these two equations using algebra, solving two equations with two unknowns, you take V0 and calculate 1/2 mv0 squared. That'll be the answer to the question. Here's problem 30 from chapter 31 from chapter 24. model a hydrogen atom as a sphere with some radius r. And we'll take r to be 1.2 Bohr radii. Your problem might have a different number, but it'll be something of the order of the Bohr radius, because that's the characteristic size of a hydrogen atom. And calculate the mass density of the atom. Now remember, density is mass over volume. So density is always mass over volume. What's the mass of a hydrogen atom? Well, a hydrogen atom consists of one proton and one electron. So the mass is one atomic mass unit. Atomic mass unit is 1.661 times 10 to the minus 27 kilograms. So that's the numerator. What's the volume? It's a sphere, so it's 4/3 pi r cubed. And r we're taking to be 1.2 Bohr radii. You can look up the Bohr radius in the textbook, or you can just do a Google search. What is the Bohr radius? And you get a value for the density. Now, if you compare a single hydrogen atom to, let's say, liquid water is H2O molecules, all kind of close together. So in fact, the characteristic density of liquid water shouldn't be too far away from the density of one single hydrogen atom. Well, everybody knows the density of liquid water. It's 1,000 kilograms per cubic meter. So the answer that you get should be something not too far away from 1,000 kilograms per cubic meter. Wait and see what you get. Here's a more difficult problem having to do with X-ray production. So this is problem 68 in chapter 24. What wavelengths would Moseley have predicted for K alpha X-rays from the three missing elements, Z equal 43, 61, 75? You'll have to read the section on X-ray radiation. I think it's section 5. I'm not sure, but you'll have to read that. The X-ray spectrum, let's see, I spelled Moseley wrong here. This should be Moseley. The X-ray spectrum has a continuum. That's from Bremsstrahlung, and it has characteristic wavelengths. Those are called the characteristic X-rays. There are a whole set of these characteristic X-ray wavelengths which depend on what atom it is. And you can calculate, using the Bohr model of the atom, you can calculate, at least to a certain approximation, the energies, and from that, the wavelength of the energies of the atomic states, and from that, the wavelength of the photons that are produced when there's a transition from an upper energy level to a lower energy level. So the experiment that's described in this section 5 is to hit the atoms with high energy electrons. That electron will knock out one of the electrons in the atom, leaving an ionized atom. That leaves an empty place, an empty shell for an electron. So a higher energy electron will drop down into that empty shell, and that radiates a photon. So the process is this: electron plus a nucleus, call it A, goes into an electron plus an ion in an excited state, plus another electron. So here's the electron that was the projectile. here's the electron that was the projectile, but it knocked out another electron, so there'll be another electron, leaving behind an ion, but the ion won't necessarily be in the ground state. So the ion will be in an excited state where there's a hole, an empty energy level. And then one of the higher energy electrons will drop down into that lower empty shell and radiate a photon, because a very common electron transition emits one single photon. And that photon will have a high energy. So that photon will be an X-ray. And now the theory of the K alpha X-rays, Moseley developed the experiments, did many, many experiments to measure these characteristic X-rays. But the theory of it was based on the Bohr model. The photon here will have an energy h times the frequency. H frequency is the energy of a photon. And it's just like a transition between hydrogenic energy levels. It's the hydrogenic energy 13.6 electron volts times 1 over n final squared minus 1 over n initial squared. So if this is K alpha X-ray, that's where the final state is an excited state, like it might be a state with principal quantum number 2. That's the initial state. The final state is the ground state. That's the state with principal quantum number 1. This is assuming that the electron that was knocked out of the atom came out of the ground state. And so n equals 1 is empty. The most likely thing to happen is that an electron in the n equals 2 energy level will drop down into that empty n equals 1 orbital. So that's the 1 over 1 squared minus 1 over 2 squared times 13.6 times the charge of the nucleus squared. Only it's not really a nucleus, it's an ion. So the interior positive charge is 1 electron charge less than the charge of the nucleus. So what we should really use for the charge of the nucleus is really the charge of the nucleus minus that electron which was ionized. So Z minus 1 squared times 13.6 electron volts, that's the ground state energy, binding energy of an electron in a hydrogen atom. H is just Planck's constant, that's universal, so you can look that up anywhere. And so you see this equation tells you F. Now the problem doesn't ask you what's F, the problem asks you what's the wavelength. So there's one more step to go through. From F, which you calculate here, you have to get the wavelength. But remember, we're talking here about a photon. Gamma is the usual symbol for a photon. Its wavelength is the speed of the photon, that's the speed of light, divided by the frequency. Because a photon behaves in some ways like a wave with a wavelength and a frequency. And wavelength times frequency is speed. Now, these 3 Z values were very special at the time of Moseley. At the time of Moseley, they had the periodic table, but there were some missing elements. They didn't have all the elements. And so Moseley would observe the frequency or observe the wavelength and determine the Z value. And he'd say, look, our periodic table is missing certain Z values. Z equals 43. That came to be known as technetium. Z equals 61. That came to be known as promethium. And Z equals 75. That came to be known as rhenium. So, this is a little more advanced problem. So you have to read section 5 kind of carefully, but this sort of shows how to go through the calculation. Now there's an exam coming up. This is Physics 232. So the exam, this homework assignment is due Wednesday. So this homework assignment is due Wednesday. That would be April. That's for I guess this is Monday the 8th. So Wednesday would be the 10th. That's the homework assignment. And you've probably done a lot of the homework problems because it actually covers 2 chapters, chapter on modern physics and the chapter on atomic physics. That then leads to the 3rd midterm exam the next day. So Thursday will be exam 3, which will be these 2 chapters, 23 and 24, and the 2 previous chapters on optics. So remember to make up your help sheet for that exam 3. It'll be just like the other 2 exams. It'll be online at 7 p.m., 70-minute time limit. And you can use a help sheet.